Okay, that's good. All right, so last week we learned lots and lots of words and concepts about multiplicative thinking. Yes, things like unitizing and composite units and all that stuff. So what I want us to do this week is to dig deeper into what that looks like in a sort of a learning situation. Okay, so what do those words mean when you're trying to learn this stuff? Okay, so we're going to work our way through 7 different activities, which will give you a taster of what learning multiplicative thinking looks like. So we're going to start right at the beginning and we're going to work through some activities. Some of them we'll be able to do together online. Some of them won't work so well online. Okay, so you can then try them later on your own. Okay, but doing them online, because we need things like counters and stuff like that. It doesn't always work. So we're going to do these 7 activities. And this would be an ideal sequence for how you would learn multiplicative thinking. So if we had a person and we could sit them down and say, right, we're going to teach you multiplicative thinking from beginning to end, this is what it would look like. Okay. But obviously that doesn't happen in real life because we learn this stuff gradually and we learn it as we get older. Okay. But because we're doing this as adults, we can sort of do this as a sequence and see how it works. All right. So that's what we're going to do. The other thing is I haven't given you notes today because I don't want to spoil any of the activities. You'll get notes afterwards, after we finished, to support the session. Okay. Right. So let's see. Last week we looked at different ways of representing multiplicative thinking as we when we got to the end of our session. So the first thing that we learned about was when we start learning about multiplicative thinking, we start learning about things as equal groups, okay, in different ways. So we start learning them as a context, with actual physical things, and then we might start representing them with circles and dots and counters and things like that. So that's the first place we're going to start. This is the bit that we can't do so much together because it's quite, it needs to happen in real life. Then we're going to move on to how we can move into using arrays for our thinking about multiplication and division, and what things that we need to show children, what kinds of questions we need to ask, etc. Then we're going to move into a simple area model, and then we're going to look at the more abstract area model. So this is the process that we're going to go through with different activities as we go through today. Okay. Sorry about the coughing. So let me explain what the screen is all about. So at the top here, we've got 1A. So these will be the tasks that we're doing as we go along. And when you get your notes, you'll be able to see those, the notes that will match against the video that we're doing as we go. All right. So the first place that we start with children is not even at equal groups. We start asking them to count in multiples. So we ask them to start skip counting. That's where we really begin this idea of multiplication and division. And so, for example, we could do a very simple thing like if we were in a group or in a club, we could say, how many fingers in this room? So we would ask one child to put up a hand like that, and we'd say to the children, how many fingers? Yeah. And so we'd get different answers coming back of, well, it's 1, 2, 3, 4, 5, or some of the children saying it's 5. Okay. So then we would say, okay, ask another child to stand up. So, Abo, will you put your hand up, please? Okay. So, how many fingers have you got, Abo?
5.
5. Okay. How many fingers are there all together now?
10.
10. Okay. All right. So then we would say, right, next one. Can you put up your hand, please? How many fingers have you got on your hand?
5.
5. Okay. How many altogether now?
15.
Okay. And
One.
what we would be doing is we would be watching how you're working out the 15. Yes. Are you counting them in ones, or are you skip counting, and so on? And then the last one, I'd say, Spook, can you put your hand up? Put your hand up. How many fingers have you got on your hand?
It's 5.
5. And how many altogether now?
It's 20.
Yeah. Okay. All right. And we would be watching. Yes. Okay.
Yes.
Okay. Let's put down our hands because that gets sore. So we would do that around the group. Yeah. And we would hope that somebody would start skip counting in 5s so that we could make a note of it and say, oh, look, somebody's counting in a different way. But if it doesn't come up, then we can always ask, how many fingers have we got on one hand? We've got 5. And is there a way that we can quickly count all of the fingers? Okay, so remember we did this thing about doing things quicker, or in a quicker way when we were doing addition and subtraction. Yeah. Is there a way we can do this quicker? Okay, and so then we start thinking about maybe we can count in 5s. We can count in 5, 10, etc. Okay, so this is a very, very simple. I'm not going to spend a lot of time here because most of us do a lot of this work anyway. Yeah, we do a lot of skip counting work, counting in multiples. But this, I want you to know that this is kind of where you start with a process. Yeah. Okay. So then, and there's conversations we can have about how we can count more quickly. And then what we want to do is to start. Okay, so there's also an important thing at this point. Remember last week we talked about a composite unit. Yeah. What we're trying to get the children is to see that this 5 is a composite unit. It's a group. Yes. The 5 of the hand is a composite unit. Yeah. So by saying, can we count them more quickly, and how many fingers have you got on one hand, we're sort of starting to get this idea of this is a thing. We've got one hand, it's got 5 things on it. Yeah. Okay. So really important that is starting to think about composite groups. And then, of course, what we want to do now is to start pushing children to making equal groups. That's the next thing that we need to think about from a multiplication point of view, because if we're talking about groups and composite units, then we need to start making groups, and they need to be equal in order for them to be useful for multiplication. Okay, so a very simple example here. There's 20 strawberries. Okay. There's 5 friends. So you can see I'm also throughout today, hopefully we're using the idea of 5 all the way through as our number of units. Yeah. So there's 5 friends and I've got 20 strawberries. We could say to somebody, can you help me share the 20 strawberries? Okay, so we could give children counters at this point and say, well, the counters are the strawberries, or we could give them stones or sticks or whatever. Yeah. And we could ask them to share that. Okay. And then we would watch again, how do they do that? Do they share it one stick, one stick, one stick, one for each person, and then go back and do one stick for each person until they've done it for 5 people? Or do they go, okay, let me put 2 in and 2 in and 2 in and see how it goes. And then I'll put another 2 in, another 2 and another 2. See how are they doing the sharing? Are they sharing it one by one, or are they kind of using some kind of multiples to share it out? Okay. Because that again tells us where they are in their thinking of what they have got in their minds. Yeah, use your counters to help work out how many strawberries we will get each. And so we want them to make the groups. The more important thing here is making the groups. It's not really the answer. We're not interested really in the answer, but the answer would be 4. Yes. So each person would get 4 strawberries. But we're more interested in the fact that the groups are equal. They're not, one of them hasn't got 6 and one of them hasn't got 2. Yeah. And that how the children have made the groups up. And then there's an important question here. Is this an equal share? Does each person get the same amount of strawberries? So if there is a child who hasn't done it equally, then this is a really important question to say, well, okay, so how come that person's got 6 and this person's only got 2? Okay, is that fair? Is that equal? Has everybody got the same amount? Okay, and then you would say, can you fix it so that everybody's got the same amount? Okay, so it's more about, so this whole process is about making the groups, watching how children do it, and making sure they're equal, and then getting them to asking questions to get them to think about making sure that everybody gets the same amount. All right. Now, this does seem a bit like division, because it kind of is. Yeah, because division and multiplication are the opposite of each other. Yes. So we kind of sharing, but then at the end of it, we can say, well, I've got 5 people, and each person has got 4 strawberries, and therefore I've got 20 altogether. Yeah. And I had 20 strawberries. I shared them between 5 people, and each person has got 4. Okay. So they can start immediately seeing the relationship between division and multiplication. Okay, now this is going to extend. So hopefully now the children know that we've got 4 strawberries each, and we used 20. So in the next question, I say, okay, now I've got 23 strawberries, and I want to share them with 5 people. Okay. Can you help me share them? So you might need them, they might need to go through the process again of sharing and making equal groups. And then hopefully they're going to go, this is not going to be an equal share. Yeah. So there's going to be, what are we going to do? There's going to be, everybody's got 4, but there's going to be these 3 left over. So what do we do with them? It's not equal otherwise. Okay. And then the next stage is to push it even a little bit further. And we say, right, we've got 24 strawberries between 5 people. But this time, do not make the groups yet. Can you predict or guess if this will be an equal share? So you can see the process. We've gone from a number where there's going to be equal sharing. Then we've done an example where there's not going to be equal sharing. There's going to be some left over. Okay. And now we're asking them to predict something before they actually prove it. Yeah. So we're hoping now that some of the children at this point will be able to say, well, it's not going to be equal because beforehand we had 23 and it wasn't enough to give an equal share. Now we've got 1 more, it's still not enough. So we're hoping that there's going to be some explanation that they can come up with. Okay. And then we can say, well, how do you know? Share the strawberries, check your thinking. Okay. So we've got this thing about that it's important that everybody gets an equal amount, and that sometimes there's a bit left over, and then we have to decide what to do with that bit that's left over. Okay. But when we've got things that are equal, then we can work out how many there are, and then we've got some extra bits that we can do something with. Okay. So this is, you can see how even this very simple thing of having a group of items that we can share, and by just changing the number each time, we can actually push the way that they're thinking about something very gradually, and how we ask them to do it. So guess, predict, estimate before you actually do it. Think about it, what's going to happen. Okay. We're starting to get into that mode of just thinking about something in our heads before we do it. Okay. So these are 2 very straightforward introductory exercises that would tend to happen in, grade R, grade 1, grade 2, perhaps, that get children into thinking about counting in multiples, composite units, and about sharing things and making sure that we have equal groups of things. Okay. Now we can start obviously they'd need lots of exercise and lots of practice with this, and lots of different kinds of contexts, different kinds of examples, different numbers of things, etc. They wouldn't just do one exercise or one activity. but we are moving through this quite quickly. So once they sort of comfortable and they understand this idea of equal groups and they can use it to multiply and to show division, then we can move on to the next very big step. Okay. This is like an interim now between groups and arrays. Okay, so it's a lovely exercise because it jumps you from making groups into using a bit more structure so that you can then introduce arrays at the next stage. So let's imagine that we've got some cards. This first card here shows some dots, and then we've got some other cards here which are turned over, so we can't see how many dots there are on those cards. All right. So I'm going to tell you we can see 5 dots. So the unit we are working with is 5. We are working with 5 things within a composite unit. So I've told you that there's 5 dots. How many 5s can you see? Can you actually see with your eyes? So you can say it if you want, or we can assume that you can show me your hand if you want to, or say it. I don't mind which one you want to. So how many 5s can you see?
5. It's 1 5.
Yeah, that's the key thing, isn't it? Yeah, you can see one group of 5. Yes. Yeah. So that question, so I've told you there's 5 dots, but the question is how many 5s can you see? I can see 1 5. Yeah. Okay. So the next question is, how could you work out how many dots there are in total? Because remember I said some of these cards were turned over, so we couldn't see them. Yeah. So how many dots there are in total, those ones that you can see and those ones that are hidden. Okay. So now what we're doing, if you remember last week when we looked at the spectrum, we are forcing children to work with stuff that's visual, but we're also working with things that are hidden so that they can start imagining what it looks like in their minds in order to work things out. Okay. So how could you work out how many dots there are? So at this point, you could give them some time, and how many different ways could you work out a solution? So I'm going to give you a minute. Okay. Think about how you could work out how many dots there are in total. I mean, you're an adult, you know the answer. But is there some ways, if you think like a child, that you could work out how many dots there are in total? Okay, so I'm going to stop the recording for a moment. And I'm going to give you a minute just to see if you can think of, well, obviously how many there are, but how did you work it out? We're adults and we know it's 5 times 4. But another way could be that a child might say, if there's 5 and we've assumed they're all the same, yeah, this one might be double 5, so that might be 10, yeah, plus another double 5, which is another 10, which 10 plus 10 is 20, yeah. So a child might use a doubling process, yes. So you guys have used skip counting, but they may also use doubling if they know that, yeah. Okay. And then there might be the one who knows their number facts already and goes 5 times 4 equals 20. It depends on the age group. Yeah. Okay. So very important things that you guys mentioned here. So the first thing is that we've got a group, how many 5s, that was the first thing. And then you all made the assumption and you stated it that they're all the same. Yeah. That's important, that they'll have the same structure. That's the only way that you can work out how many there are. Because if they're not the same structure, then how do you know? Yeah. Okay. So that's an important part as well. Okay. So the groups are equal. That's the key thing. Let's see what we can do next now. So we're still working with this group of cards. Let's see if there's some follow-up questions that we can ask children to think about. Now, these ones would really get them thinking. How many dots would there be if I had one more 5? So we established that there was 20, yeah? How many dots would there be if I had one more group of 5 or one more unit of 5? What would the answer be?
You mean one more group of five dots?
Yes, another group of 5 dots like this. So if I added another group of 5 dots to this, how many would there be altogether?
25.
25.
25. Yeah. Okay.
Oh.
So we know there's 20. And if I added one more 5, then I'm just adding 5 on top of it. So I'm just asking now, I haven't put the card there. We're asking the children, and I'm asking you to use your imagination. What would happen if I put another group of 5 there? Yeah. So you can see how we're building up these mental images constantly with these groups in our heads. Yeah. Okay, let's see. We know that 4 5s is the same as 20. We worked that out. So does that mean that 5 5s must be 25? So yes, we've answered that. Yes, if we added another one, we had 5 groups of 5, that would be 25. Here's a question. You know, we've said that we've got 4 cards, 4 groups. What does that 4 tell us? Why is it important? Is that something that we can actually answer? Can we put that into words?
The 4 tells us how many times we should count in 5s. We should skip counting 5s.
Yeah. So remember last week we were talking about making a copy or a photocopy of something. Yeah. We're going to make this copy of this 5 unit. We're going to do it 4 times. Yeah. Okay. So the 4 is important because it's part of our sum. It's going to be how many times we do it. And what does the 5 tell us? And why is that important?
The 5 also tells us in which multiple should we count in, and in like the groups of 5, like they are important because we are now counting in 5s, and if you're not counting in 5s, whereas you're instructed to count in 5s, you will get a wrong answer.
Okay. So yeah, sorry, carry on.
Yeah, so you should be able to group according to the number of maybe if say in 5, you should maybe be able to group in 5s.
Yeah.
It's important so that you can get an accurate answer.
Okay, so yes, so we're working with 5. So this is our composite group, if you like, isn't it? It's our composite unit that we are visualizing in our heads, this group of 5. Yeah. And it's the number of things that are in that group that we have to work with. Yeah. But so there's 5 individual things in the group, and we make one group of 5. Yeah. Okay. So these questions are digging out those 2 bits in the sum, which are the 5 times 4. Yes. We're wanting to find out before we even show children the number symbols. We're digging out these questions that there's 2 bits that we have to deal with. Yeah. We've got to deal with how many items there are in a group, how many groups there are, and then we can get a total. Okay. All right. How many dots would there be if we had 2 more groups of 5? So how many we've got here? We've got 20 here. Again, we're just pushing this. I've asked how many we would have if we had 1 more. How many would we have if we had 2 more groups of 5?
30.
30. Okay. How did you work that out?
From the rows of 5 that we have, I added 2 rows with 5 dots, and then I skip counted in fives according to the number of rows.
Okay.
And then it got me to 30.
Did you start from 5? Start from the beginning in 5, 10, 15, 20. Yeah. Okay. So you did 5, 10, 15, 20, 25, 30. Okay. Another way that you could do it.
Another way could be plus 10.
Yeah. Yeah. So we've got 20 plus 5 plus 5, or 20 plus 10. Yeah. Depending on how you think about it. Yeah.
Yeah.
So constantly, so if I had Grekli in my class, for example, and you were going back to the beginning and counting from 5, yeah, I would say, can you think of a quicker way of doing it? Yeah, like we did with when we were doing the number lines. Can you do it with less jumps? In the same thing here, can you think of a way of doing it without going back to the beginning? Yeah. And so you keep pushing, yeah. Okay. And then this is a lovely one as well. How many dots would there be if we had 1 less 5?
1 less 5 from the 20.
From the 20, from this, yeah.
15.
Okay, how did you work that out?
15.
How did you work that out?
You would remove 1 row.
Okay. So what did you say? 20 minus 5?
20 minus
or
5.
Did you count 5, 10, 15? How did you do it?
20 minus 5.
20 minus 5. Okay. Okay, so again, there's more than one way of doing it, isn't there? Yeah.
Yep.
Okay. Right, so you can see that this little group of cards, this one activity, could take a whole session, yeah, because there's a lot of questions to ask, there's a lot of discussion, and for children who might not get it, they might still need to build out the 5 with counters and try it and see if it works, yeah. But you can see that it's a lovely jump between making equal groups, as we were doing before, where we're sharing stuff out. And we're now saying, right, well, we've got equal groups. Let's put them in a structure so that we can imagine things. Yeah, we can imagine more, we can imagine less, etc. Okay. So now the big jump comes. All right. So what I've got here, if we were doing this in real life, in IRL, I would have this on the board, or I would have it on a desk or something like that. And I'd have a printed array, and I'd have a piece of paper over the top of it, which is the yellow bit. Okay. So I'd again have 5 dots showing, and then I'd have the yellow piece of paper over the top, hiding something underneath. All right. And again, I would say, always establish how many dots can we see altogether so far. What can I see visually? Okay, so 5. Now you see the little thing is moving slightly there. It did move slightly like that. Okay, so you would take the paper away and then quickly put it back on again. All right, so that they get a quick view of something underneath there. Yeah, you can see it quick. Okay. We could then say something like, using your mathematical imagination, how many dots are in the second row, do you think? Yeah. How many dots are in the third row? So now we're also starting to introduce the word row as a terminology. Okay, so we might need to explain what that is. But we can say we're starting to imagine how many are in the second row, how many are in the third row. Okay, so hopefully the answer would be 5. Because they've had a glimpse. Okay. And now we're starting to introduce an idea of one way of thinking about it. If we double 2 5s, okay, if we double 2 5s, think about what that looks like, and add 1 more 5, will that help us work out how many dots in total? Okay, so would that help us work it out? If we double a 5 and then add 1 more, would that work? Put your thumbs up if you think it would work. Yeah, okay. So double 5 would be 10, would be those bits that are hidden, perhaps, yeah? And then another 5 on top. So we would have 15 in total. And then the question is, we're asking them here, before we take away the paper, in your mind, think about what this would look like, okay? So we are starting to get them to visualize these things in their heads, and taking away the idea that we have to be able to see everything to be able to solve a problem. We can do some of it by visualizing, by imagining. Okay. So then you would take the piece of paper away. So if you've asked them to visualize it, then take the piece of paper away and then we check it up. Yeah. So how many rows can you see? How many are in each row? And then record an equation or a sum for this. So if we wanted to, then we could say, okay, how could we write a sum for this? So it would be 5 times 3, because we've got 5 items in each row times 3 groups. Yeah. So we could be forcing a written symbolic sum or equation at the end of it. Okay, so it starts by showing something, using your imagination, thinking about what the whole thing might look like, and then coming to check that this is what it looks like and how many have we got all together. Okay. So it's this whole thing. So the whole purpose of these activities or these exercises are to get away from the completely visible to using the imagination, so that when we start working in the more abstract, when we take away the dots and everything like that, we've got ideas of what these things look like in our minds. Okay. And this is often the step that gets missed out, is getting people to practice using the imagination and to practice the visualization bits. Yeah. This is normally, we jump from groups to arrays and we expect children to understand what it's all about in between. Okay. But we know that we have to make these things obvious to people. We have to make these things explicit. Otherwise, they won't see the connections. Okay, so that's the third activity. So we're going to continue with arrays now, and they're starting to get more abstract. Okay, these are tiles that we might see in a bathroom or in a kitchen, somewhere. And so we could show these two tiles, these two sets of tiles, and then we could ask questions like this. What is the same about these two rectangles? Now notice this time I'm using the word rectangle. Okay, so I'm using the word rectangle instead of array. What I'm trying to show children as well, what we're trying to show children here, is that an array is actually a rectangle. Okay, so we're crossing over boundaries between, we were learning operations of multiplication and division here, but we're also talking a little bit about space and shape and geometry. Yes, all these things connect. This is a rectangle. It's also an array. Okay, so we've got two questions here. What is the same about the two rectangles and what is different? So I want you to just have a quick think about that. I'm going to stop the recording and then we'll take some ideas. We're going to do this. Okay, so a great place to start, something that's real, tiles, and even if you could find some tiles and you take them into the club or whatever, would be great to do that. So now we could say, can you make another rectangle that uses the same 12 squares? And it would need to be different to those two. So just think quickly about what you could do. So you're still using the same 12 squares if they're all individual, yeah? Could you make a rectangle that looks different to those two? What would it look like?
I'm speaking, but I'm on mute. It would be the same as, almost the same as the second one, but looking vertical, horizontal,
Vertical. Okay, vertical.
vertical. Sorry. Yes.
Okay, all right.
So it would be 2, 4, 6, 8, 10, 12.
Okay, so how many rows would it have?
It would have
Use the words rows.
six,
Yeah.
six rows
And
of
how many in each row?
2.
2. Okay.
Yeah.
So you see how I'm pulling out. I can see what you're saying. I'm supporting you now with the right words.
Words.
Yes. Yeah.
Yes.
So that you do that
Okay.
with the children as well. If they say, oh, it would be 2, 4, 6, 8, you say, okay, right, let's use other words. Let's see if we can use the structure. Yeah. And so you start introducing the words into the conversation. Yeah. Okay. So
Yes.
Abba's turned the second one around and to 6 rows and 2 in each row. Yeah.
Yeah.
Any other ways that we could do it?
I think for me it will be 4 rows
Yeah.
with 3 in what? Yeah, it will
Yeah.
be 4 rows. 1, 2, 3, 4. Yes.
Yeah. With how many
With
items
3.
in each? With 3 in each. Okay.
With
Right.
3 in each. Yes.
Yeah. Okay. So both of you, so Abbo's taken the second one and turned it on its side. Spoo, you've taken the first one and turned it almost.
Yes.
Yes. Yeah.
Yes.
Okay. Is there another way? I'm pushing you now. Is there another way?
12.
12 what?
No, I'm thinking, sorry.
Okay, sorry.
It will be 2, 6, 8, 10.
Okay, imagine that these are individual little squares that you can break apart. Yeah, so you've got
Yes.
12 individual little squares that you can break. Can you make another rectangle?
Mhm.
There. It's 2, 3, and 4.
Okay, Spoo, follow your
8.
line of thought. So you're looking at kind of at the factors there, yeah? And you say there's the factors of 2,
Yes.
factors of 3, factors of 4.
3. That's 4.
There's
Yes.
what other factors have we missed out then if we're working with 12?
6. Yeah.
Okay, 6.
Yeah.
So Abbo got that one. She had 6 rows, yeah?
Then it's 12.
Aha, 12 what? 12,
12.
what does it look like?
It will be 1 row. 12 rows with 1 in each. Or
1 column and 12 rows.
Okay.
yes, 1 column.
Yeah, okay, yes. So
Do we call that an array?
yes, it's still a rectangle, just a long skinny one.
Yes.
Yeah. Yeah. So, okay. So I love the process that you went through there, and I've deliberately recorded it because it was important. You were sort of going through the numbers that worked with 12. Yeah.
Yeah.
So that's what it might look like. Yeah.
Yeah.
Yeah. So the other ones that you did where you turned them on your side, great. Okay. But it could also look like that. It's 1 row with 12 items. Yeah. And you could have turned it the other way around as well. Yeah.
Yeah. Yeah.
So now the next thing when we do this type of exercise with children is we now make sure we get all of them. Yeah, so we get all the factors if we like. Yes. So if we say to the children, right, still using these 12 tiles, how many different rectangles can you make? And how will you know when you found them all? Okay, so we're now making sure that we've got all of them from 0 to 12. Yeah. So how do we do that? Well, the best way is to give them a piece of paper, grid piece of paper like this with squares on it. Yeah. Use a grid, a pencil, and you draw your answers. Yeah. So I know that you probably haven't got grid paper with you, but if you can get some and you can practice this later. So let me show what it might look like. Yeah. So they might start, right, I'm going to start with 1. So I'm going to draw 1 row and I'm going to put 12 items in it. Okay, that still gives me 12 tiles. Yes. Then I'm going to move to 2. Does 2 work with this? Yes, I can do it. I can do 2 rows with 6. Okay. Then I'm going to move to 3. I can do 3 rows with 4. Okay. Then I'm going to move to 4. I can do 4 rows with 3. And in between here, there would have been a thought process of, can I do it with 5 and get equal groups? No, because it wouldn't be an array. Yeah. So I leave 5 out. Can I do it with 6 and still end up with equal things? Yes, I can. 6 rows, 2 in each. Then I would go, can I do it with 7, 8, 9, 10, 11? Can I get equal ones? Yeah, because don't forget, if we were doing this with grade 3s or 4, they might not know these are factors yet. Yes. So we would encourage them to go through 4, 5, 6, 7, 8, 9, 10. Can you do it and end up with equal things to make an array? And then eventually you get to your 12, which would look like that. Okay. So you're encouraging them to start with 1, because there's always going to be something times 1. Yeah. And then you work through the different ways that you can make rows and columns until you get, and that's how you make sure you get all of them. Yeah. Okay. So that you are now approaching this problem from a logical point of view. Yeah. And if you were then working with grade 4s and 5s, you could then start saying, well, these are your factors of 12. Okay. This starts to show what the factors are. With younger kids, you wouldn't use that word, obviously. Okay. So that's a useful thing, is to have some of this grid paper and pencils and to be able to go through that process. Yeah. Okay, but you guys got them all. So you can give yourselves a give yourselves thumbs up or a clap. All right. So that was exercise number 4. Do you want to have a quick break, or shall we carry on?
Yes, a quick break, please.
How long? How long?
Just
5 minutes.
minutes, I don't know.
5.
Till 1:30.
Till
Yeah,
half
till
past.
1:30.
Okay, all right.
Yes.
So let's have
Yes.
till 1:30. Get a drink, go to the loo, let Spoo do whatever he needs
Yes.
to do to get out the car,
Okay.
and we'll meet again at 1:30. Okay.
Right.
Yes.
We could now ask children to do that same process with, how many ways are there to make rectangles or arrays with 24 squares?
Yeah.
Or how about 18 squares? And so we give them paper, pencil, and a grid again, and we ask them to go through that process of making sure that they find all the different ways to make something that's got 24, something that's got 18. Okay, you could use 36. So any of the numbers that have got lots of ways of making arrays. Yeah, so choosing 9, for example, is not a good example, because there's just 2 ways to do that. Yeah. So the numbers that you choose to get them to practice are the ones that have got lots of different ways of doing it. Numbers with lots of factors, if you want to use the proper mathematical term. Yeah. 24, 18, 36. If you're pushing with older kids, 72, 96, those types of things. Yeah. Where there's lots of different ways of doing it. And they draw and they work through from 1 all the way through and make sure they've got everything. And then obviously, if you want to make it into a pair thing, they can talk to each other about their thinking. They can talk to each other about various things that they've done on the paper. Okay, so it's a nice exercise because it starts, where does it start? It starts by looking at something visual. Yeah. You're looking at things that are the same and the different. It goes through lots of things that are to do with geometry as well. Then it starts thinking about different ways that you can make different arrays. Okay, Obviously, if you were going to do this with children as well, you wouldn't do it all in one session. It would be spread over different things. But we're not talking about using it in the clubs at the moment. All right. So let's have a look at number 5 now. Now, this one's going to be tricky for you to try and do because we haven't got an array for you to practice with. So let's talk you through and see how we get on. So we're still working with arrays, but now you can see the arrays. This array has got much bigger. Yeah. So this is actually a 12 by 12 array, 12 rows with 12 items in each row. Okay. So what we would do is we would give this to the children, or you could show it, you could demonstrate it. And then you cover part of it with pieces of paper, okay, to show a smaller array. So for example here, we could say I have covered part of this with paper to make a 7 by 5 array. And then I can go through and I can use the terminology to make sure everybody's happy with it. It's 7 rows and 5 columns, or it's 7 rows with 5 in each. And then I could say how many dots in total. Okay, and so at that point, now I'm asking perhaps you, if you want to work it out, how can you work this out? How many dots in total? And there's going to be obviously different ways of doing it. Who would like to share? We're pushing you to think of different strategies. Yeah? Okay. Because skip counting will work, but it's going to start taking time, isn't it? You know, 5, 10, 15, 20. And how do I keep a track of that? Yeah. Okay. So you can see by changing the size of the array, changing the total, we're starting to push things, making the thinking happen. You can see all these things are designed specifically, yes? They're like when we were doing the addition and subtraction. The numbers and the things that you use are so important for pushing constantly to the next step, yeah? Okay, so let's see what happens next. So we've still got the same array. Now I could say to you, if you had one in front of you, I would give you different arrays to make. Yeah, so if you had this in front of you and you had 2 pieces of paper, I could say to you, I want you to make an array that is 6 columns, 6 rows and 3 columns. Yeah, and you would then put the pieces of paper, and then as a facilitator, I would come around and check that you've done it right, or you can check each other, and you would say how many altogether, etc. Okay, so you would just give different examples and you would go around and check and let the children talk to each other about what they've done and how they've worked it out. Okay. Then I might say do one that's 3 rows and 7 columns, or 3 rows with 7 things in each one, and get you to make it, get them to check it, talk about it. How did I work out the total? And you could carry on. Yeah, as many examples as you wish. All right. So it's quite a nice one because you have a printed array, and just by using pieces of paper, you can make smaller ones that are going to get them thinking about things in different ways. You notice this one at the bottom, 4 rows with 4 items or 4 columns. So what shape is that going to make? It's going to be a rectangle or something else? Do you think?
It's a square.
It's going to be a square. Is a square a rectangle?
It's a rectangle.
A special case of a rectangle, isn't it? Yeah.
Yes, it's just a special case of a rectangle.
Why?
Because the square has equal sides.
How many?
4 equal sides.
How many equal sides does a rectangle have?
A rectangle has 2 equal sides.
2 opposite equals. Yes?
Yes.
Yeah. Okay.
Yes.
So a square still fits that requirement.
4 equal sides.
Yes. Okay. So again, I've put that one in as an example because it's now we're starting also to talk about square numbers, yeah, which will come up in grade, I don't know, so it's 5, 6, or 7, where you start talking about 4 squared and so on. These are now the early representations of a square number, 4 by 4. That's what it looks like, yeah. But we've also done a bit of geometry, bit of space and shape. We've defined rectangles, we've defined squares, we know, okay, so we're making sure that mathematics doesn't happen in, you know, in the Free State, you have lots of grain silos, don't you? Where you put the grain in, those big, tall silos, yeah? We're not making sure, we're making sure that the mathematics doesn't happen in just one silo, yeah? We're making sure that the mathematics connects between them, yeah? So if we can bring in the idea of square numbers, we can bring in something to do with geometry. Let's bring it in. Let's pull in what everybody knows. Yeah. You don't have to start teaching square numbers at this point, but you can start saying, oh, that's an interesting shape. That's different to the other ones that we've done. Okay. Yeah. So these things are all there to start making connections. All right. So still continuing with this idea of using this big 12 by 12 array, we can now extend it by asking them not to create a number of rows and columns. Now we're asking them to think about, oh my gosh, use 24 dots and make your own array that's got 24 dots in it. So now we're tipping it on its head again, and it was similar to the previous activity that we did. Yeah. How can I make an array which has to be either a rectangle or a square that has 24 dots in it? And so they're all going to come up hopefully with the different layouts. Yeah. The 3 by 8, the 6 by 4, the 2 by 12, whatever, they're going to come up with different ones. Because now we're not giving them the structure, we're giving them the total. So if you think about the structure of a multiplication sum, where we've got the number of items, how many times we multiply it by, equals the product or equals the total. By doing this, we're working from the end bit and we're working backwards. Yeah. In the previous examples, we were working with the structure and we were working with the first 2 numbers in the multiplication sums. Okay. So it's always good to approach things from different angles because it makes you think differently. Okay. So again, the lovely numbers that have got lots of different ways, 24, 36, 72, 96, all those types of numbers, yeah. And then we can push this a little bit further. So because now children are going to make lots of different types of ones, or you would make different types of ones, we want to represent your array using words and symbols. So what do I mean by that? So for example, if you'd made an array with 6 rows of 4, you could record this as 6 4s equals 24. So that would be words. You could write it like that. And then the symbols would be 4 times 6 or 6 times 4. Yeah. Okay, depending on which way you've done it. So that's the symbols and your words. So now we're pushing it to say, okay, this is the representation. We're now making it more abstract by making it into words and into the symbols, the number symbols. Yeah. So again, we're pushing just a little bit. We've turned it on its head, asking them to make different configurations with a number of dots. And now we're taking it another step further. And now we can take it an even further step. So now we say to whoever, make your own choice of array, anything you like, describe it to someone else, describe what it is, how many rows, how many items, what's your total, etc. And then ask them to make up a word problem to match the array that they've made. Ooh, now we really have to think about it. Yeah. So for example, 4 lions live in each cave and there are 6 caves. How many lions altogether? So that would be if they'd made a 6 by 4 array and they could make up a story to go with that. So we're stretching it to make up your own array, describe it to someone, so talk about it, and then find a context to make it make sense. Yeah. That would be hard, but it's a good thing to try. And then using that same thing, that same whatever they've made, we could ask them to turn it on its side. And so we can look at the array from the different angle. And this is when we start practicing the commutative property, where we can say 4 times 3 is the same as 3 times 4. It's not the same, it's the same answer. We still get 12, yeah? But we can turn the thing on its side. The array looks different, but we still got 12 as our answer, okay? So we can then start using the arrays to pull in an important mathematical piece of learning, which is the commutative property, which we learned about last week. Okay, sorry, there's an example. Yeah, so we could start, if we started with 5 rows of 7, and then we turn it on its side, it's 7 rows of 5. Okay, we still get 35 as the answer, but it's a different shape rectangle, and the number of rows with things in are different. Okay, so that's exercise 5 or activity 5, which again is quite an extensive one that could take place over a number of learning segments, with different ways of getting people to think about how arrays are made and how you describe them, whether you describe them with words, word stories, word problems, whether you describe them with symbols, etc. Okay, now we're working into the area method. Okay, so now there's a big jump. Okay, so we've done quite a lot of examples with arrays, which is where we would spend a lot of time with children. And now we're going to jump to the area. Now, before we start this, I just want to read this to you because this is important. Understanding the diagrams that we use for mathematics is not always as natural as we think it might be. So we might think, oh, okay, this is an array and I understand it. We cannot assume that children understand that. Okay, we have to explain to them what a row and a column is. We have to explain to them that it makes a rectangle. Yeah, an array is not a shape that's got different numbers of things in each row and column. Yeah, so we have to actually make these things specific and say them to the people. Yeah, explicitly showing the connection between concrete representations, so things that we actually do in real life, and the diagrams that we use. We have to make the connections between these things and how those things connect to our thinking in our mind. We have to make that explicit. We can't just assume they're going to get it. So like when we were doing the empty number line things, I said to you, you cannot go into a club and start teaching this immediately. There's too much stuff that they need to know about an empty number line first before you can use it. And the same applies to all these things that we're doing for multiplication and division as well. You have to teach the stuff and you have to make the connections and make the representations so that it can become more abstract. So we're talking about this because now we're jumping from an array to an area method or an area model. Okay. So I'm going to ask you to try and do this. Create a model. Now you can't do this where you are representing 5 16s using something like stones or counters. Obviously you haven't got stones or counters. Maybe you could draw what that would look like on paper. 5 16s. What would that look like? Draw it on paper if you can. I'm going to give you a few minutes.
Hi, book. Just follow 16 about 5.
Where?
And manje our balance here.
Go 16 about 5, okay, go 5 about 16.
About six, about
560.
about 5, about 16. 5 is long.
Or 5 about 6. Yeah, represent 516. Or 16
Yes.
about 5, guys. 1, 2,
About
3,
5.
4, 5, 6, 7, 8, 9, 10,
About 16,
11,
about
12,
5.
13, 14. Yeah. 16. 1, 2, 3,
I
4,
have a
5,
5 about
6, 7,
16.
8, 9. Ah,
All right. So this is kind of an array. This is a very structured version of it. Yeah. Okay.
Yes.
So I think yours was probably the closest to the structure. Yeah. Everybody else had 5 rows with 16 in all, had a different layout, which we can't see just yet. Yeah. So if we'd been working with arrays, this would be something that we would expect, but there's also nothing wrong with the other ways that people have shown it. Yeah. Okay. Except that fact, perhaps with Spoo's one, it's a bit more difficult to work out the total because it wasn't in some kind of a structure. Yeah. So that's a good talking point. Yes. Because Spoo's is an accurate representation of it, but it would be hard to work out the total number from Spoo's because things weren't in a structure. Do you see what I mean? Yeah. So it would be a really good way of saying, well, what's the difference between Abo's one and Spoo's one, and which one would help us work out the total quicker? Yeah. We're going to ignore yours for the moment, and we'll see. We'll come back to yours later. Okay. So the thing I'm trying to say as well is that it doesn't matter what children present you with, what people present you with. You can use it as a way of saying, how can we use this now to work out our solution or our answer? Yeah. And which one would make it easier to do and why? Okay. So let's see. The reason we chose those numbers, that I chose those numbers, yeah, is it took you quite a long time to draw that, wasn't it? You had to count your 16s. It was a bit of a mission. Yeah. And so I chose those numbers on purpose to make it like, oh my gosh, seriously, does she want me to draw 16 things 5 times? Yeah. So again, it was on purpose so that I could ask this question, is there a more efficient way to represent it? Okay. So if we think about Spoo's way, was quite, we heard you counting every time, 16, another row, 16, another row, 16. Yeah. So we could hear you counting. We couldn't hear Abo's counting, but I'm assuming that she kind of just counted 16 once and then she made 5 rows. So maybe that was a more efficient way. We couldn't hear that. Yeah. Obviously, is one we're going to see shortly. All right. So a more efficient way, a quicker way to represent it. So let's see what happens. So what we can say to children now, and I'm going to say to you, is that we can draw a rectangle instead of an array. Now, this is now why it's been useful to talk about rectangles and arrays as we've gone along, because now we're going to use a rectangle. If we put a label on each side, we can now say that our rectangle will represent an array, but without showing all the individual parts. Okay, Abo, show us your table again, please, your grid. Okay, so that is an array because we can see all the individual little squares. Yeah. So what we're going to do is take a leap from that to making it into a rectangle, which looks like that. Yeah. And we're saying in our imagination, this is why it's so important that we've done all the other work up to now. Imagine that we have got 5 rows. Whoops, that we've got 5 rows and we've got 16 in each row. Imagine it. We don't have to keep drawing all the circles and the dots and the lines. We can imagine it now. And these labels tell us what's inside it. Okay. This is called an area model. And the important thing about this again is related to geometry, to space and shape. How do we work out the area of a rectangle? Does anyone know? If I said to you, this is a rectangle, what's the area of it? What would it be?
5 times 6, 16.
5 times 16. Yeah. Okay. So again, there's this crossover between rectangles, between arrays, and now we're sort of getting into even to the point of saying, well, this is also about working out the area of the entire rectangle by using our imagined rows and our imagined columns. Yeah. Okay. So if you take this model, how could you use it to think about solving 5/16s in different ways? Because 5/16s to work out is actually quite difficult, isn't it? We don't really know what 5/16s are. It's not a fact that we know. Yeah. Can we use the area model to work out what the actual answer is without counting every single dot or line? So now, Abo, Spoo, earlier I said, remember that thing that you did with 7 times 5? Yeah. Chle, remember what you've just done here. Yeah. In your example. See if you can work out how you could use this area model to work out the answer to 5 times 16. Now, I'm going to give you one example, and then I'm going to ask you to try different ways. Okay. But you've all already done this in some way. So here's an example. I can say that 16 is equal to 5 plus 5 plus 5 plus 1. Do you agree? 15 plus 1. That's 16, yeah? And I've got my 5 rows here. And I can use the area model to say, okay, 5 times 5 is 25. 5 times 5 is 25. 5 times 5 is 25. 5 times 1 is 5. And then I can do some work at the bottom. 5 times 5, 5 times 5, 5 times 5, 5 times 1, 25 plus 25 plus 25 plus 5 equals, ta-da, there's the answer. So there's an example, okay? I want you to see if you can think of at least 2 different ways of doing this to get the answer to 5 times 16. So I'm going to give you, what's the time? It's 7 minutes past. I'm going to give you to 20 past to try this. So that's about 13 minutes, yeah? Try it on your own if you want. Talk to each other. See if there's different ways that you can use this model to solve this problem, ones that make sense to you. Okay.
Okay.
Try.
Yes.
I'll turn off the video and audio.
Okay.
Okay, so this one was breaking the 16 into 5, 5, 5, and 1, yeah?
I also broke it into 7, 7 plus 2.
Okay, because the 5 times table is quite easy, isn't it? You know, so 7 times 5, we know we know these number facts. So 7 and 7 and 2 is also easy, isn't it? Yeah. If it was the 6 times table, it might be more difficult, and that would determine how you break it up. Yeah. Yeah.
Yes.
Okay. So this one is taking it and saying, okay, 10 times 16 is easy. I know that. is 160.
Okay.
Yeah. And then, because I know that 5 is half of 10. Yes. So half of 160 is 80. So I can do it with doubling and halving as well. Does that make sense? Yeah. Because my 10 times table is also an easy table to know. Yeah. Okay. So that's one other way. You said 10 and 6, Abo. You could also do it as
Yes.
10 and 5 and 1. Yeah.
Okay.
Same thing. Yeah. So 10 plus 5 plus 1 is 16. 50 plus 25 plus 5. Yeah. Now notice what I'm saying here and what I'm getting you to say as well is that it's 5 times 10 is 50. 5 times 5 is 25. 5 times 1 is 5. Okay. And then we're adding up all the separate bits. We are using multiplicative language. 5 times 10. Okay. And then I asked the question, would breaking it into 10 and 6 work? And that's exactly what Abo said at the end. Yeah, 10 and 6 is the same. 5 times 10 is 50. 5 times 6 is 30. Okay. So those were some of the examples I had. You guys have got your 8 and 8. You've got your 4, 4 and 4, and you've got your 7, 7 and 2. Now, let's look at, can you look at your phone if you can and look at the WhatsApp group? Yeah.
Okay.
So Leslie drew the initial picture. Can you see it? It was 5 groups of 16. Yeah.
Yes.
Okay. So I said, great. Okay. Makes sense. My question would be, how does that help you work out the total? Is it possible to skip count in 16s? Yeah. And then you responded by, yes, I can work it out by saying 16 plus 16 is 32, 16 plus 16 is 32, 32 plus 32 is 64, 64 plus 16 is 80. Now, what is the difference? So yes, you got the answer. What kind of thinking is that versus the thinking that we've been doing with the area model?
What kind of thinking is that? I don't know how to explain that.
Okay,
even in this example,
It's a hard thinking.
Okay, so I would say that that is additive thinking. You're still using addition to solve the problem. Repeated addition. Yeah. So it's a really good example. So remember that the one thing that we have to get people to learn when they're doing multiplicative thinking is to get away from repeated addition. Yeah. To get to this idea of seeing things as groups. Yeah. So it's fine. Yes, you got the answer. 16 plus 16, 16 plus 16, 32 plus 32. It's all addition. Yeah. There's nowhere in there that I can see clearly that it's about a number of groups. Yeah. Okay. I'd have to work out quite hard what's the number of groups that I'm working with to get to that multiplication thing of I've got my group and how many times do I need to replicate it? Yeah. Okay. And because you've written it as addition, I can see the thinking perhaps is that you are using addition to solve the problem, which is not a problem, but it becomes more difficult when the numbers and things get bigger. Yeah. So if I'd said to you it was 5 times 375, yeah, then it becomes more tricky. Yeah. I'm not criticizing. Okay. This is a learning thing. Yeah. And it's a really good example of showing how we need to push to get away from addition so that we can actually work in by using multiplication, this idea of the groups and multiplying by how many numbers. Yeah. Does that make sense? Yeah. Because
Yes.
even with something like this, we can still see that I've got 5 of something, I've got 5 of something, I've got 10 and 6, I've still got 16. I can still see what my groupings are. I've got 5 times 10, and then I add another 5 times 6. I can see that I've got 16 little items that I have to multiply by 5 each time. Yeah. Okay. So in these examples, you can still see I've got 10 and 5. That's my 16. I can see it quite clearly. Yeah. Okay. And because we're thinking, we're using multiplication to think here. We're saying it's 5 times 10. It's not 10 plus 10 plus 10 plus 10 plus 10. Yes. And it's not 5 plus 5 plus 5 plus 5 plus 5. Yeah. We're actually saying it's multiplication. Yeah. It's multiplying. So that's the leap, if you like. Yeah. Okay. So oh, she's gone. I hope that's not because of what I said. Nope, she's back.
I will.
No.
Okay. I thought you disappeared because you didn't like what I said. All right. So what we've been doing here is called the distributive property. Okay, so it's another thing that's another mathematical concept that allows us to take a number like 16 and to break it into bits that help us to work with it easier. Okay, it helps us to distribute it across things. So numbers can be broken up to help us think flexibly about problems. And the area model allows us to think in this way. It allows us to break things up, and we can see the breakups in the model and represent it. So the distributive property is important because it relies on our understanding of how numbers are made up, exactly as we were doing when we were doing addition and subtraction on the number line. We used, depending on the numbers and the question, we broke the numbers up differently depending on what they were. Yeah. And the same thing applies here when we use the distributive property. So for 16, we've had 8 plus 8. We've had 4 plus 4 plus 4 plus 4. We've had 10 plus 6. We've had 5 plus 5 plus 5 plus 1. Yes. We've had all of these different things make up 16. Yeah. So we understand what parts make up the whole to give us different units that we can work with. And it helps us to use things that we know, which all of you did. Yeah, I know 8 times 5. I know 4 times 5. I know 6 times 5, whatever. Yeah. And it helps us to work out an unknown fact, 5 times 16. So we use the facts that we knew to work out the facts that we didn't know. Okay. And it's very, very important. So what we did with the area property and that example that we've just done is about using your existing knowledge to solve something that you do not know. Okay. Which leads us to our final exercise, our final activity, which is a number sense activity. Because we have to do a number sense activity every week, don't we? And it's perfect at this point. So if I know, now we did this last week, so I'm going to give you a different example this week. Deriving facts, that means that we can make facts from things that we already know. So it helps children build number sense. It helps for looking and using relationships between numbers and between operations. So if we know something about multiplication, we also know something about division. And working out the unknown from the known teaches problem-solving strategies as well as logical thinking. Okay. So this process that I'm doing with you every week is very important. So your fact for today is this. Here's a known fact. 4 times 10 is 40. Do you agree, first of all? 4 times 10 is 40. Okay, good start. Yay. Okay. Right. what other facts can you work out by knowing 4 times 10 is 40? Now, we did this last week with 3 times 5. Do you remember? Okay. So I'm going to give you 3 minutes. If you know 4 by 10 is 40, what other things can you work out? You might already know some facts, but you can also work other stuff out by working from that. Okay, so I'm going to give you 3 minutes. You can work on your own or you can work together, and then we'll come together and look at your responses and finish off. Yeah?
All right. Okay.
We'll take yours. All right.
Okay.
So you might know, if you know 4 by 10, you might also know, just without even thinking about it, that if you turn it round, commutative property, think about an array, 10 times 4 is also 40. And then the 2 division facts that go with that. 40 divided by 10 is 4. 40 divided by 4 is 10. Okay. And then if I said to you, can you prove that? The best way to prove it would be by using an array, a 4 by 10 array. Yeah. And making a 4 by 10, then turning it around so it becomes a 10 by 4, and then talking about how you can divide the 40 into 10 bits with 4 in each, etc. Okay, so if I asked you to prove that, those facts, you could perhaps use an array to prove that. Okay, so when we finish today, I want you to think about how you could prove that with an array. Make it 4 by 10 and see how these facts look. Yeah. Okay, so those are 4 facts that come straight out of that one thing. Now let's see something a little bit more complicated. So this is what Abba was talking about. Yeah. If I know that 4 by 10 is 40, then if I start using some place value on either side, yeah, I can make numbers. So if I make the 4 into a 40, it becomes 400. If I make the 10 into 100, it becomes 400. If I do place value on both sides, 40 times 100, it becomes 4,000. If I take the 10 and I make it 4 times 1, it becomes 4. If I go into decimals, yeah, or fractions, it becomes 0.4. So all of this is about place value knowledge and applying the place value to either the first number, the second number, or both of them in different ways. Yeah. Okay. So again, if you know your place value, you don't even have to think about these. You're just going, okay, I know if I know the basic one, I can work all these others out by going up into the hundreds and thousands and going down into my decimal place value if I have to. Yeah. Then here's my basic fact. I can do some doubling and halving, which you did with your array models. Yeah. I can say 2 times 20 is 40 because, whoops, sorry, I hate it when it does that. If I take half of that and I double that, it's still going to end up with the same thing. It's still going to end up with 40. Or if I double the 4 and halve the 10, it's still going to end up with 40. Now, if this is making your mind explode, go and see if you can do it with an array, like we did earlier. Make an array of 4 by 10 and look at 40 and then say, okay, well, I've got 40 dots or I've got 40 things in my array. How can I arrange them differently to get 40? I can arrange them as 8 by 5 or I can arrange them as 2 by 20. I still get 40, but it's about doubling and halving. Okay, so when you halve and double a number, the total, the product, the end stays the same. And I can prove my thinking using an array. And this is what I want you to try and do today. And then obviously we can also extend it and say, well, if I know that 4 times 10 is 40, if I add another group of 4, one more group of 4, and then I've got 11 groups, I've got 44. We did that earlier when we were looking at the little cards. We added one more group of 5. This is adding one more group of 4. Yeah. So these are the things that I can work out by knowing this basic fact. Okay. So, did you guys have any other examples that you would like to share?